Project 5.2 deals with the SR latch. This expands on the idea of propagation delay and glitch, and it relates it to a real-life application of a circuit known as the SR latch, which is a basic circuit used for memory, and can later, if you change it a little bit, it becomes better. But it's very, very basic, so we look at the very basics, and the idea here is that if you have this thing called bistable state, which is how you can store information. It's called stable because once it's in a certain state, Q and Q naught will always be different, or at least they should be, for it to be bistable. And you got these feedback loops, which also is the reason that you can make it bistable. Now, the idea is that when you want to set the information or store something in Q, if you want to store a 1 in Q, these are active low. So you would send a low, you would assert low, and the set input, which would drive the Q to a 1. And if later, a second later, drove the set input to a, or actually I said that backwards because it's active low. Once it's in a set state, it doesn't matter what S is. It doesn't matter if it's a 0 or 1. It'll stay in that state. And conversely, the same thing is true with reset. Reset sets Q to 0, Q naught to 1. It doesn't matter after that point if you change the reset input to 0 or a 1. It's going to stay in that state. Okay, now this project introduces the idea of how propagation delay can cause a glitch in this circuit, where you end up getting meta stability, where your Q will oscillate between 0 and 1. And the way that it's stated in the project file is that the metastable state will be triggered when neither the set operation nor the reset operation propagates through the whole cell before the cell changes to the hold state. Okay, and the hold state's here, 1, 1. Now, actually doing the project, it gives you all the code, it gives you the test bench code, and it gives you the model Verilog code, and it builds in this 1 nanosecond propagation delay, and then here's the feedback loops where it has inputs and the outputs looped together. And then it wants you to actually look at the timing diagram, which I have here, and it wants you to see the propagation delay, which you can see here, where there's 1 nanosecond propagation delay from the point that that S is asserted low to the point where Q gets its value of 1. And so it wants you to look at that point, it wants you to see the propagation delay, and then it also wants you to see this metastable state that is triggered. So it goes through and it says what happens when you put a 0 on S. When you put a 0 on S, it's going to drive Q high, and it's going to put it into a set state. So if you then later change S to a 1, it doesn't care, it doesn't change anything. Now if you assert the reset input, it's going to drive the Q low, and it does show QN goes high, so these are always supposed to be opposites. Now if you after you assert the reset, if you change it to a 1, it doesn't do anything to Q. It just stays the same because it's in a stable state. And then if you assert both at the same time, both the Q and N get a value of 1, and because there's a feedback loop that screws things up, so then when you deassert it here, when you drive both high, S and R high, you get this oscillation of values for Qn and Q, which is called the metastable state, and that's something you don't want and can be fixed in other flip-flops using clocks and whatnot in other configurations. And that's the whole idea behind Project 5.2.